Today we're going to talk about applications of singularity analysis. As with the rational and meromorphic asymptotics, really what we're going to be talking about is general schema that apply to whole families of combinatorial classes and show how those schema can be used to derive asymptotics for many of the classes that we considered early in the course with just a few simple calculations. So this is our next to last lecture. Next time we'll talk about saddle point, which is for generating functions that have no singularities. But we're going to talk about lots of the combinatorial classes that we considered in part A, where we have a generating function equation that's not rational or meromorphic, that has singularities other than poles. And last time we saw a general approach to dealing with such functions, but that lies underneath some very broadly applicable schema, and that's what we're really going to be talking about today. So the first one is simple varieties of trees, and we talked about that a couple of applications last time, so let's just look again. So we start with this transfer theorem that's proved with the singularity analysis process developed by Flajolet-Odlyzko in 1990, but that all that mechanism kind of lies underneath. So the idea is we have what's called a simple variety of trees where the combinatorial construction is Z with a product, either a Cartesian product or a star product, of a sequence, a recursive sequence of the same class, where there's some modifier that says what sizes of sequences to use. So there's this idea of lambda invertible, where there's a few technical conditions, but the main one is that we define a function phi, which comes right out of the symbolic method from the construction into a generating function equation. So the sizes of sequences that we use translate into different functions phi. So the construction defines the function phi, and that's a so-called characteristic equation. Lambda is the root of this equation. Phi of z equals lambda equals z phi prime of z. So if we have that value lambda, then we have the coefficient asymptotics and the function phi. And it's a function of, first of all, the coefficient growth is just phi prime of lambda. The exponential growth is just phi prime of lambda to the n. And then the constant is a simple calculation involving the second derivative evaluated at lambda. And it's also the case that the singularity analysis gives us an approximation to the function itself. And that's going to work out to be important in applications later on in this lecture. So it says that a simple variety of trees has a square root singularity, and we can accurately approximate both the function and its coefficients at that singularity. And as always with singularity analysis, we can take these approximations out to arbitrary many terms. In lecture, we'll just work with the tilde approximation. And this applies to any kind of tree, virtually any kind of tree, and we'll look at several examples next. So important note is, as I just mentioned, that the singularity analysis gives you not only the coefficient asymptotics, but also approximation of the function near its dominant singularity. And that's automatic. This is a schema that works for any kind of sequence. And so, as usual, in most applications, what we're going to be focusing on is the calculations involved in the coefficient asymptotics. And these are quite simple calculations. For example, we looked at general trees. And again, back in part one of this course, we looked at general varieties of trees, and there are certainly a lot of calculations involved in finally getting out the coefficient asymptotics. There's information in between in terms of it's the Catalan numbers and Stirling's approximation and other things, but doing that calculation from scratch involves certainly a fair amount of discrete mathematics. And the idea of analytic combinatorics is we can get that coefficient asymptotics in just a few simple steps. And this is a review of last lecture, but maybe some people are watching this lecture for the first time. So if G is the class of rooted ordered trees, that's just the construction is Cartesian product of Z and a sequence of trees. A tree is a root in a sequence of trees. That immediately translates to the generating function equation, G of Z equals Z over 1 minus G of Z. Now we're going to apply the theorem for simple variety of trees. And what that means is we first have to identify the characteristic function. That's 1 over 1 minus u. We compute its derivatives. So that's easy, 1 over 1 minus u squared and 2 over 1 minus u cubed. And then we get the characteristic equation, which is 1 over 1 minus lambda equals lambda over 1 minus lambda squared. That's setting phi equal to lambda phi prime, and you get lambda equals 1/2. And then evaluating the characteristic function and its derivatives at lambda, we get 2, 4, and 16, and plug in those values, we immediately get the coefficient asymptotics. 4 to the n into 3/2 over 4 square root of pi. So that's our pattern, that's our template for analytic combinatorics that we strive for every problem. Now have a construction, take us right to a generating function equation, take us right to coefficient asymptotics. And that's what the simple variety of trees transfer theorem does for this example. So what about binary trees? That's another familiar example that we've looked at since the early lectures in part 1 of this course. Well, one way to construct binary trees is to say it's an external node, or it's an empty tree, or a binary tree on the left, or an empty tree or binary tree on the right. You might have been expecting some construction like a binary tree is a node and a sequence of either 0 or 2 binary trees. That's another way to construct binary trees. We'll actually look at that one later on. But this one translates right to the generating function equation, b of z equals z times 1 plus b of z squared. If you have z times the function involving the original on the right, then that's simple variety of trees. So we take the simple variety of trees theorem. We have to identify the characteristic function. In this case, it's 1 plus u squared. Compute the derivatives, 2, 1 plus u, and 2. Characteristic equation, phi of u equals u phi prime of u, and that works down to this equation. The lambda squared and the 2 lambda, it comes out lambda equals 1. And then evaluate the characteristic equation and its derivatives at lambda, and we get 4, 4, and 2 in this case. So that means the exponential growth is 4 to the n, and the 2's cancel, and we simply get 1 over square root of pi, 4 to the n into the 3/2. Again, immediate transfer from the construction to a generating function equation to coefficient asymptotics. That's analytic combinatorics. Here's another example review from last lecture. That's those first 2 examples we know how to do with relatively elementary methods. This one, examples like this are much harder. So this is unary binary trees where a tree has either 0, every node has either 0, 1, or 2 children. So a tree is a node plus a sequence of either 0, 1, or 2 trees. So that's simply expressed. Immediately translates to the generating function equation, m of z equals z times 1 plus m of z squared. That's a simple variety of trees. So we identify the characteristic equation, 1 plus u squared, compute the derivatives, 1 plus 2u and 2. Characteristic equation is you set phi of u equal to u times phi prime of u and solve. In this case, it's lambda equals 1 again. 1 plus 1 plus 1 equals 3. 1 plus 2 is 3. Then evaluate the characteristic function and its derivatives, add lambda, and we get 3, 3, 2 in this case. So phi prime is 3, so that means 3 to the n is the exponential growth, and in this time the constant turns out to be square root of 1 over square root of 4 pi over 3 n to the 3 halves. So all simple varieties of trees are going to have n to the 3 halves. They're going to have exponential growth, and the difference is what's the factor and what's the constant. Again, straight from the spec to the generating function equation to the coefficient asymptotics without anything in between. Now there is a lot of machinery under there in terms of the singularity analysis process. Lagrange inversion was in there to prove this. Quite a bit of sophisticated mathematical machinery was necessary to establish this transfer theorem, but once it's proved, it's very easy to apply, and that's the theme of this whole lecture. We have some very broadly applicable transfer theorems that are quite easy to apply and can lead to the analysis of all sorts of combinatorial structures that would be very, very difficult to analyze otherwise. And just to finish the story, this simple variety of trees also works for labeled structures too. So we looked at Cayley trees, so that's labeled, rooted, unordered trees. And so there's n to the n minus 1, and we looked at this in lecture 2. So this is the analysis that we did in lecture 2, and I'm just going to flash through it. So it's a Cayley tree is a root connected to a set of trees, and for the labeled structures, the transfer from the construction into the generating function equation, it's for exponential generating functions, and set means take e to the power, so we get c of z equals z e of c of z. And then in lecture 2, we used Lagrange inversion theorem to get the coefficients out, and that eventually getting to n to the n minus 1 for the number of Cayley trees. So it's n factorial times that coefficient is n to the n minus 1. So in that certainly a valid way to extract coefficients. But my point for this lecture is that we don't need different tools for every type of trees. We have one theorem that works for all types of trees. So let's look at Cayley trees from the standpoint of a simple variety of trees. Same construction. It's a node is a node star product with a set of nodes. So that same translation, c of z equals z e to the c of z. But now as a simple variety of trees, this one's even simpler than the ones that we just looked at. We can, it satisfies z star product sequence or set of something, and so we immediately get the characteristic function phi of u equals e to the u. The derivatives are all e to the u. So as long as our generating function has this form, then the rest of the theorem comes through. So our characteristic equation is e to the lambda equals lambda e to the lambda, so lambda's 1. And then plug in to evaluate the characteristic function at the value 1, you get e all the time, so phi double prime over phi is just e, and phi prime is e, so it's e to the n, so immediately you get 1 over square root of 2 pi e to the n to the minus 3 halves, immediately. Boom, 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 for Cayley trees, using the same theorem that we use for general trees or unary binary trees or any kind of tree. Just a matter of figuring out the characteristic function, doing the derivatives, solving the characteristic equation, plugging back into the formula. It's a very general and significant theorem. You don't need to know the underlying mechanisms behind it in order to get coefficient asymptotics. You can work at a different level, which is a level closer to the problem. How do I construct my structure, and how can I estimate the number of structures of that size? And then I can use that information for all sorts of things, like taking the log to find out how many bits they're needed, or other information, and we'll talk about examples in a little bit. So just as an aside, to show that everything's hidden under the covers, even Stirling's formula is hidden under the covers. We looked at the exact derivation through Lagrange inversion. And then in this lecture, we talked about the approximate derivation through singularity analysis. The exact one says we get n to the n minus 1. The approximate one says we get n factorial e to the n over square root of 2 pi n cubed. Those derivations are a proof that that holds, and that's just Stirling's formula. Counting Cayley trees in two different ways gives us Stirling's formula. That's one way to look at it. But that's really, in today's context, what we're interested in is that we took four pretty different types of trees and got full analysis of them, including down to coefficient asymptotics, using the same theorem. That's an introduction to schema based on singularity analysis.